In this screencast, I'll be discussing isothermal reactor design based on material in Scott Fogler's book. The starting point is we can just talk about the flowchart for how we handle reactor design problems. Of course, the starting point is the mole balance that was described in an earlier screencast, where we have the molar flow rate of a substance going into a reactor, the molar flow rate leaving a reactor, the rate of consumption by reaction or generation, and that equals the rate of accumulation of material in the reactor. And based on that equation, depending on which type of reactor we have, there are three ideal balance equations, or design equations. For a batch reactor, we have no flow, so we just have the accumulation term and the generation term. And putting those together, we can relate the time required to get to a certain point in the reaction to the rate of reaction and the conversion. So this integrated expression. For a CSTR or a mixed flow reactor, we can relate the volume to the desired fractional extent and the rate of reaction, and it's at steady state, so there's no net accumulation. For a plug flow reactor, it looks very similar to a batch reactor actually, and I'll say more about that. But if we take our balance equation and we do a balance over a differential slice, we end up with the equation that the volume is equal to the molar flow rate going into the reactor times this integrated expression of 1 over the rate of consumption of a species. So with that in mind, we have our design equation. We need a rate expression. If it's not given, so this direction in the flowchart, of course we need more information. And you would need to be able to develop a rate law one way or another. Now, if you were really starting from scratch and you were working with a new system where you didn't know anything about it, you may have to do experiments to determine the rate law. You may be given information in a problem, maybe about a different type of reactor, a different type of experiment, and you can use that in order to determine what the rate law should be. Once you have that, you need to determine concentration expressions as a function of conversion. If it's a liquid or a constant volume batch reactor, we can write the expressions in this kind of form, where the concentration depends only on conversion. So for example, for species A, it's the initial concentration times 1 minus conversion. If it's species B, we need theta, which expresses the initial concentration to B to A, and then we need stoichiometric coefficients to be able to relate the concentration to conversion. If it's a gas phase reaction, in general, it may not be constant volume, so we need this factor epsilon, which has to do with the initial mole fraction of A and the net number of moles produced per mole of A consumed. If the temperature changes, that will affect the concentration of a gas phase reaction, and if the pressure changes, that will affect it. So we may have to consider those factors as well, but if we know that information, we would insert it into the rate law, and we then hopefully end up with something we can integrate. If we can't do it symbolically, we can do it numerically, and that's how we approach these problems. So you have most likely seen many examples of reactor design types of problems. Here's an example, and I'm not going to go through these in much detail. I assume you've seen many examples and done many examples yourselves. So for example, if we have a liquid phase second order reaction occurring in a batch reactor, we're given the half-life is 40 seconds, how long will it take to reach 90% conversion? So the starting point is to begin with a mole balance. For a batch reactor, this is what it looks like in terms of conversion. The rate law, since it's second order, the rate of consumption of A is a rate coefficient multiplied by the concentration of A squared. From the stoichiometry, we can say the concentration of A is Ca naught times 1 minus the conversion. So we insert that into our design equation here. So we have the rate of change of conversion being proportional to the 1 minus x squared. And it also depends on K times Ca naught. So the next step is to separate the variables, so we'll have something that we can integrate. In this case, we want to get terms that depend on conversion together, and that's what we have on the left-hand side of this equation. That's straightforward to integrate. We get 1 over 1 minus x being the general form of that integral. We put in the specific limits of x, the final conversion that we're interested in, and 0 at time 0, so that's just 1. The right-hand side of the equation is trivial to integrate, really, because it's a constant, so it's k times Ca naught times time. So that is our integrated expression. So we can use that to relate conversion to time at any point. So to actually answer the question, the first bit of information was that the half-life is 40 seconds. So the conversion at that point is 0.5 and the time is 40 seconds. That allows us to determine the other variable in this equation, which is k, the rate coefficient. Oh, sorry, k times CA naught, which is 0.025 inverse seconds. And then using that, we can determine the time to get x equal to 0.9. And that's 360 seconds, or 6 minutes if you prefer different units. So that's the type of equation. This one's relatively straightforward, of course, because it's just a single reaction. It's irreversible, but that's how we handle these types of reactor design equations. Another type of reactor that we may be interested in is a CSTR. And you may have seen this kind of design before, so I'm not going to dwell on it too much, but I do want to mention the Damköhler number, which is one of the new concepts that's introduced in section 4.2 of Fogler and is useful in general. So if we have a CSTR, this is the design equation, one form of it, where we can write the space-time tau being equal to the volume of the reactor over the inlet volumetric flow rate, and that's equal to the difference in the initial concentration minus the final concentration over the rate of consumption of A. And that's at the exiting concentration of the reactor, because it's a well-mixed reactor, so that's the concentration everywhere after the feed has been introduced. The rate of consumption for a first-order irreversible reaction is a rate coefficient times the concentration of A. So if we put that into this expression and rearrange it, we can write that the concentration of A is Ca naught over 1 plus tau times K, or the conversion is tau K over 1 plus tau K. Notice that in both of these expressions we have tau times K, and that is tau has units of time and K has units of inverse time, because this is a first order reaction. So this is a dimensionless number, and for a first order reaction this is the Damköhler number. It relates flow time to reaction time scale. In general, we could define Damköhler number for any reaction, and we'd want it to be equal to the rate of consumption of A based on the initial conditions in the reactor, divided by the inlet flow rate of A divided by the volume. That will give us two terms that have the same unit, so it will be dimensionless, and it's essentially a ratio of time scale versus diffusion or transport scale. In this case, it's convection because we have flow of reactants occurring in the reactor. If we're doing diffusion problems, the Damköhler number can also be useful, where we may define the reaction timescale versus the diffusion timescale. And as a rule of thumb, a small Damköhler number on the order of 0.1 will give a small conversion on the order of 10%, whereas a large Damköhler number, and if we're thinking about orders of magnitude, on the order of 10 or more, is going to give a high conversion, so on the order of 90% or more. Of course, there are always exceptions to these rules, and maybe that's not an exact quantitative prediction, but that's the right order of magnitude. Now, another thing for CSTRs that's new in Chapter 4, and you may have seen before, but it's worth mentioning, is that if we have constant volumetric flow rate for CSTRs in series, we can write the design equations. And of course, we do this sequentially, just going through one reactor at a time. So for example, for the first reactor, just based on a similar expression to what I had a couple of slides ago, the concentration leaving the first reactor, because it doesn't matter what follows, is the inlet concentration divided by 1 plus the Damköhler number, or tau 1 times K1, for that first reactor. And in general, the volumes of the reactors don't have to be equal, and the temperatures don't have to be equal. So tau and K can be different from reactor to reactor. So in that general case, we would need to begin with a design equation again. So for example, if we have a second reactor, we could start here, where the volume of the second reactor is the flow rate entering minus the flow rate leaving, divided by the rate of consumption of A in that reactor. So we can write that as V naught, the volumetric flow rate into all reactors, which is the same as the volumetric flow rate leaving, times Ca1 minus Ca2 over K times Ca2, and rearranging that expression leads to a concentration from the second reactor of the concentration leaving the first reactor over 1 plus tau 2 times K2. But if I insert this expression for Ca1, that leads to this expression in terms of Ca naught, so the inlet concentration for the entire sequence of reactors. So the concentration leaving the second reactor is the feed concentration over 1 plus tau 1 K1 times 1 plus tau 2 K2. And if we had more reactors, if we had a third reactor in sequence, we could then divide by 1 plus tau 3 times K3, and so on for any number of reactors. If the temperature in volume are constant among reactors, then tau and K are equal, and we can write the concentration leaving the second reactor as Ca naught times 1 plus the Damköhler number squared. And for n equal volume CSTRs in series, concentration leaving the final reactor is the feed concentration over the quantity, 1 plus the Damköhler number to the nth power. So that gives us a way to say what we would have for any number of reactors. And in the limit, as the number becomes infinitely large, we would get the same result as for a plug flow reactor, actually. To give you one other example that applies the concepts in this chapter, and this has nothing to do with the CSTR, but this is just sort of skipping around the chapter and doing things that are new. If we look at a non-constant volume plug flow reactor, this is discussed in section 4.4 of Fogler, if you have that available to you. But for example, if we need to consider epsilon not being 0, so there is a volume change due to reaction, then the concentration of a species is given, so for species A, is given by Ca naught times 1 minus x over 1 plus epsilon times x. And I talked about epsilon in the last screencast. It was, it can be given by an expression like this, where of course I'm assuming there are A and B being reactants and C and D being products. This can be generalized to any case, but it's the net number of moles produced per mole of A consumed, and that's multiplied by the inlet mole fraction of A. So if we have a second order isothermal plug flow reactor and we'd like to integrate the design equation, of course this is general, it applies to any situation, and we need to insert our rate expression in terms of conversion. Well, it should just be the rate coefficient for the reaction times the concentration of A squared. But I can use this expression for the concentration of A. So I end up with K times Ca naught squared times 1 minus x squared, and in this expression we also have 1 plus epsilon x, so that ends up in the numerator here. So this is my design equation, and it's possible to integrate it. So you can use Wolfram alpha if you choose. Fogler has a table of integrals of this type in the back of his book. You can find integral tables online, or you can just use your knowledge of calculus. But one way or another, it's possible to integrate this, and this is the kind of expression that you get. So it's another example where a symbolic solution is available. Of course, it's more complex than if epsilon was 0, but in the limit, as epsilon goes to 0, this term will go away, this term will go away, and this term will go away, and so we'll end up with x over 1 minus x being proportional to the volume, which is what we would have predicted if we had a constant volume reactor. So this is just one example that happens to be integrable and gives this particular solution. You could work this out for other orders of reaction and for variable values of epsilon. So I don't get cut off, I'm going to stop this particular subset of the screencast here and come back and talk about a few other examples where we can apply the design equations to different situations that you may not have seen before, depending on what course you've taken before. So I'm going to stop here.